Thank you all for coming to this talk. I'm Feng Chun, a principal engineer at Huawei. Today, I will show you how PyTorch enable high-performance training and inferencing on instant NPUs. Here's a quick look at today's agenda. I will start with the challenges we face when integrating diverse computing hardware into PyTorch. When walk you through the solutions we have developed using ASIN as an example. As we know, PyTorch has always been committed to enable deep learning across different kinds of hardware. But for many third-party accelerators, integration is still a big challenge. Typically, these challenges come down to four questions. How to integrate, how to make it easy to use, how to ensure quality and stability, and how to get great performance on new hardware. Today, PyTorch supports several built-in backends, such as CPU, CUDA, and MPS. But the number of dispatch key is limited, which means it can't natively support every new hardware type out there. Starting from PyTorch 2.1, a special key called Private Use 1 was introduced. This allows any vendor to plug in their backend through a unified entry point. So for the community, it reduces the maintenance burden, and for the hardware vendors, it brings flexibility and faster innovation. Now, backends that use private use 1 are usually packaged as a plugins. That means users have to import them manually, which of course is not ideal for a large ecosystem. To make it easier, PyTorch 2.1 introduced automatic plugin loading. Using Python's entry point, PyTorch can now automatically detect and import backend plugins. So, in-tree and out-of-tree backend now behave the same, making it much simpler for users to take advantage of new hardware. Now, while the flexibility is great, it also brings some challenges around backend quality and compatibilities. When upstream change occur, key interface updates can sometimes break backend plugins. For example, on ascend, we ran into more than 10 compatibility issues in just 2 months. To address this, we built a tool called Open Registration, or OpenReg, a CPU-simulated backend connected through the private use 1 mechanism. OpenReg provides test coverage for all critical backend capabilities. It also serves as a reference example for new hardware vendors who want to integrate with PyTorch. Beyond that, under the PyTorch Foundation organization, we maintain a set of end-to-end testing projects that continuously track backend quality. These tests are automatically triggered by a pull request labeled with a specific tag, and they run on self-hosted runners provided by hardware vendors. They perform compilation, unit test, model validation, and basic functional test against the key PyTorch ecosystem project. If any issue is detected, the CI system automatically adds a comment or open a linked issue, but importantly, it doesn't block pull request merge. In eager mode, we introduce a task queue mechanism, a high optimized operator dispatch pipeline. They use a lock-free ring queue to dynamically balance operator scheduling, fully utilizing both CPU and NPU resources through compute overlapping. At the same time, a secondary pipeline manages a dedicated operator memory pool, which improves memory reuse and reduces inter-thread interference. This design alone can reduce CPU overhead by up to 50%. And for large models, we also provide NPU-optimized high-performance operators, covering most mainstream LLM scenarios to maximize compute efficiency on ascend. Next, let's talk about graph execution. We built NPU graph, which is similar to CUDA graph, and it helps reduce device idle time caused by CPU launch overhead. NPU graph provides 3 API layers: a C++ runtime API, a Python API, and integration with Torch compile. It also speed up inference and reinforcement learning workload. For example, with vLLM Ascent running Tianwen 2.5, enabling graph execution cut inference latency from more than 100 milliseconds to just 28 milliseconds, while significantly reduce CPU overhead. Starting from PyTorch 2.6, Torch NPU integrates the inductor NPU extension and provide a Triton backend for Ascent. This enables the Torch compile path with inductor and Triton on Ascent. The inductor NPU compile applies hardware-specific optimizations to the generated Triton code, ensure high execution efficiency. It also supports NPU graph tree, which can help maximize memory reuse. Together, Torch compile and the NPU graph deliver both graph-level optimization and runtime efficiency. Beyond PyTorch itself, the PyTorch ecosystem projects are also embracing multi-hardware support. For instance, DeepSpeed provides APIs for customer accelerators and operators. vLLM uses a plugin-based backend interface, which make it easier to add new hardware with minimal code changes. Today, Ascent already supports over 20 ecosystem projects, actively help to expand AI computing diversity across the industry. And finally, we'd love to invite you to join us in advancing PyTorch multi-hardware ecosystem. You can participate in the PyTorch Accelerator Integration Working Group or the vLLM Extension Hardware SIG. And if you are part of Chinese developer community, we welcome you to follow our ongoing efforts on local communities and social platforms, as we continue to grow the Chinese community and developer ecosystem together. Thank you all so much for listening. Considering there is a lightning talk, I won't be leaving time for Q&A. If you have questions or interested in our project, we can continue discuss after this talk, or you can find me in our booth. Our booth number is G1. Thank you very much.